Talked about the convergence aspect. Could you quickly define what does the convergence even mean, or what does the word convergence mean? Because there's so many aspects to convergence, and what does it mean in terms of CFD?
Yeah. Convergence is something that I think confuses quite a few beginners when they first start with CFD. The reason it can confuse beginners quite a lot is you often load up your CFD code, be it Fluid or CFX or Star, and you run your first program, and you usually see a plot of residuals from the transport equations. And they have a very typical shape where they all start up about 1, lots of colored lines, and then they drop down a bit, and then they start wiggling around and stay horizontal. And as a beginner or a first-time user of CFD, often it's assumed that when the lines stop going down and the residuals stop going down and it starts just moving across and wiggling around, that I've reached convergence. That's often what a lot of people think. And what often the next question is, well, how far down do the lines need to go? What happens if my line goes down to 1e minus 2 and then wiggles across? Is that converged? It's not moving anymore, but has it gone down low enough? And there's definitely those questions come up a lot. There's not an easy answer to them, and it's quite a frequent stumbling point for beginners. So what is often then the advice given to many people is that you shouldn't just use residuals to judge convergence of your CFD case. And as well, what does convergence mean? Is it just that the white lines are wiggling? How else do I judge that? Well, firstly, we're probably used to the idea that because we're solving some equations in an iterative manner, every time we solve the equations, hopefully our solution will continue to improve as we make continued guesses. And often the criteria that people use for convergence is they say, well, perhaps the solution that I'm getting from my next guess or iteration is staying the same. I'm not improving anymore. The residual, as they often call it, the part that's left over from your solution, that's not getting any smaller. That's often what people mean when they say convergence. And there's definitely some differences in terms of what an engineer would call convergence as to what a mathematician would call convergence, or a computer scientist. If you were a computer scientist or a mathematician, you'd want to continue running that iterative solver until the residual, the bits that's left, gets down to something that's called machine tolerance, where the number is so small that it's indistinguishable from the resolution of the numbers that the computer stores in its memory. That's what a computer scientist or a mathematician would usually go with for convergence. But for an engineer, the problems we solve are often non-linear, they're very complicated, and we often can't bring that residual all the way down to a machine tolerance. And so what people tend to do is, rather than looking at a residual, which doesn't really tell us anything, the trick is to look at the quantity that you're interested in. What quantity are you going to use as an output from your solution? Am I looking at the lift coefficient for an aerofoil, for example, or am I looking at the torque from my rotor or my propeller? That's often the thing that you're interested in. And so a better way to judge convergence is to look at the residual and to also look at the quantity that you're interested in, and look at what happens to the lift coefficient on the aerofoil as I continue to simulate my CFD code. If my lift coefficient gets to a value of 1.278, for example, and then continues to move around a little bit around that, in my subsequent work, if I'm going to say the lift coefficient is 1.2 or 1.3, then that simulation is suitably converged for your application. So that's